concept in this discussion is heat transfer coefficient, how it behaves. How do you find the values of heat transfer? Let's imagine there is an arbitrarily shaped body like this, and there is a fluid which is flowing over the body at certain initial velocity u infinity and temperature T infinity. They are called free stream conditions. Whenever there is infinity, please understand this is bulk motion, right? That represents the huge surroundings like atmosphere, its velocity and temperature. Now it is flowing over this body. So like we discussed earlier, the heat transfer coefficient need not be the same throughout the body because the conditions, those three conditions are one of those three: geometry of the body, or properties, or nature of fluid flow. Need not necessarily be same throughout the body. It's quite obvious. One part of the body may be experiencing a different condition compared to the other part of the body. Therefore, the heat transfer coefficient need not be the same or constant throughout this body. It may differ from point to point because the factors that influence the heat transfer coefficient are varying from point to point. You all can imagine these things. There is a bench, the same bench that I am giving you an example, right? Not the entire part of this body is experiencing the same effect of the fluid motion that is created by the fan. I'll take another example, right? Now I am taking the entire class as the object, right? Now, for sure, all of you will not be experiencing the same comfort or discomfort. Somebody sitting at this corner and somebody sitting in the middle and at the other corners, their experience of comfort may be definitely different, right? Because of the fluid motion, because of natural vegetation, because of the fact that three people are sitting or only two people are sitting or only one person is sitting, right? Now I am considering the entire as one single body, right? And the body at different parts is experiencing different conditions. So therefore, the heat transfer coefficient is bound to be different, at different points of this entire single body. So now, if I divide this body into many small parts, say like small part this here, let's say I am dividing this into 100 small parts, right? And each of these parts may have different value of heat transfer coefficient. That becomes local to that part, and that we call it as local heat transfer coefficient. See, for example, the same body, right, which is like this. I am telling you that I will divide, or this body is divided into many small parts. Say suppose this is dA1, this is dA2, dA3, and so on. How do I get the total area of the body? The total area of the body is integral dA. Now, integral dA is nothing but summation of the small parts. So I will add like this: dA1 plus dA2 plus dA3 and so on. If all are of same size, then simply integral dA is equal to dA. That we can write it as. So now similarly, we may have the heat transfer coefficient here as H1, here as H2, here as H3 and so on. So these heat transfer coefficients are called local heat transfer coefficients. Local heat transfer coefficient. Right? Now, how do you establish the relationship between local heat transfer coefficient and the average heat transfer coefficient over the entire body? So, for example, under assumption that the entire body is having a single fixed heat transfer coefficient, again assuming the conditions under which this body is kept are unchanging, right? So then the heat transfer coefficient is fixed. Let me assume that heat transfer coefficient as h bar, which is the average value over the entire body. Okay. So now I can write this as heat transfer rate, right? Q is equal to h bar into the total area of the body, entire area of the body, A or AS, whatever it is. If I write AS here, this will become DAS. Right? So AS into the body is at temperature. Now this body is surface is at Ts and the surroundings are at T. So therefore this is Ts minus T. Let us assume this is equation 1, where h bar is average heat transfer coefficient over the entire body. Now let me take one small part, any one part, like mentioned here, right? So the heat transfer from that small element is dq. So dq is equal to h. Here my h is local at that particular value into what is the area of that body, that small part, DAS, right? One part, this one, into temperature is fixed. Temperature is constant throughout the body. So in all these parts, the temperature remains the same, Ts, minus temperature of the surrounding fluid is same for any part or all the parts, right? So then this is Ts minus T infinity. So now if you want to get the total heat transfer rate from all parts, right, you have to integrate this over the entire area, over the total area. So therefore it is equal to integral over the entire area h DAS into Ts minus T. Now let us assume this is equation 2. Now from equations 1 and 2, from equations 1 and 2, the right hand terms can be equated, right? So h bar into AS into Ts minus T infinity is equal to integral h DAS Ts minus T. Since Ts and T infinity are constant, right, they have nothing to do with the discussion that we have. So therefore Ts minus infinity, Ts minus T infinity can be cancelled out. And what do you get here? H bar is equal to 1 by AS into integral h into ds. So this is the formula that we can use to find the average heat transfer coefficient if you know the local heat transfer coefficients at any given point. Please make it. Now look at this. This object is a flat plate. This is arbitrarily shaped body. This is a structured body. It's a flat plate. It's a flat plate of length L and uniform width. Let's say the width is 1 meter. Right? Please make a note. As shown in figure 2. For a flat plate of length L, and unit width what happens to this area AS will be equal to, see again take the case of the tabletop, length is L, I am saying the width is 1 unit, that is 1 meter. So what will be the area? Length into width. So that is L into 1 is equal to L. Now, in the direction of length, which is shown as positive x. Suppose if you take a differential length, small length dx, and that constitutes a small area from which certain amount of heat is leaving. So now, what is the area ds at that point? DAS, length into width. What is the length here? What is the length? Dx. Dx into what is the width? 1. So this is dx. Therefore, suppose if we assume this as equation 3, from equation 3, for this configuration, right, for flat plate, it's a special case that we are assuming. H bar is equal to 1 by L, because AS is equal to L into integral. Now it is integrated over x. X varies from 0 to L is equal to H, that is the local heat transfer coefficient, into what is DAS? dx. So this is a simplified version of this for a specific geometry like this. H bar is equal to 1 by L into integral x is equal to 0 to L H into dx.